In the previous classes, we have seen the BJT, and after that, we have seen the JFET. So, in JFET, JFETs were operating in reverse bias case. Like we were going to apply the gate to source voltage that is in a reverse bias, so that whatever current was flowing is going to be restricted by applying the further reverse gate to source voltage. Okay. So similarly, we will be going with the next topic, that is MOSFET. So in MOSFET, we have already seen it is of two different types. Okay, so the MOSFET, it is of two different types. So one is depletion MOSFET, or we call it DMOS. Another one is enhancement type MOSFET, or EMOS we can call it. And this depletion type MOSFET, we have seen it can operate in either depletion mode or in enhancement mode. But this enhancement type MOSFET can operate only in enhancement mode. Okay, so it can operate only in enhancement mode. That's why it is called E only MOSFET. And this can operate, depletion type MOSFET can operate in both the cases. So it is also called DE MOSFET. Okay, so in this MOSFET case, we will be going with first the depletion MOSFET, how its working is there, and then we will see some of the working operations of enhancement type. And before that, we will just go with the topic, that is MOSFET. What is basically a MOSFET is, and how this MOSFET is different from BJT and JFET. So this MOSFET is basically fabricated with VLSI technology by using technology called planar technology. Okay, so it is MOSFETs are basically fabricated with VLSI by using planar technology. So what is the meaning of planar technology? So this planar technology is the technology where a single plane or a same plane will be used for depositing different layers. Okay, that means same plane will be used for fabricating that IC. Okay, that's why it is called planar technology. Here it is MOSFET. So these three letters indicate MOS, that is metal, oxide, and semiconductor. So there will be three different layers. Okay, one will be metal, another will be oxide, and one layer will be for semiconductor. Okay, so like if this is the metal layer, this is the second layer, and this is the third layer. So it will be metal, and this will be oxide, and this will be semiconductor. Okay, so it is of three different layers: metal, oxide, and semiconductor. So because of this oxide, so the oxide thickness or oxide, different oxides can be used. So different oxide properties provides larger input resistance to this MOSFET. So, okay, so this MOSFETs we will be having larger input resistance because of the oxides we have used. So generally, we will be using SiO2, silicon dioxide, like the oxide in between the metal and semiconductor. Okay, it is also like this is metal and semiconductor, in between there is a oxide. So this oxide behaves like an dielectric. Okay, so between two conducting uh, plates there is a dielectric, so it behaves as a capacitor also. Okay, so MOSFETs behave like a capacitor. It is going to behave like a capacitor also. Okay, some other properties of MOSFET is it dissipates very less power, or we can call it is having negligible power dissipation. And similar to the JFET, so JFET was also a voltage controlled device. Okay, so this is MOSFET is also a voltage controlled device. Voltage controlled device. So here voltage control device means we are going to change, or we are going to provide input as a voltage, and we are getting the output in terms of, yes, the output will be in terms of, so here it is voltage controlled and output we are getting is current. Okay, so it is voltage controlled current source. Okay, so MOSFET will be voltage controlled current source. Similar to JFET, it is also a symmetrical device. Symmetrical device means it is having four terminals. Okay, so here if you're talking about the symbol, there are different type of symbols in case of MOSFETs. Okay, so one is like this is N channel MOSFET. It is of enhancement type. Okay, this is gate, drain, source, and this is body. Okay, if it is of P type, we will be using a bubble here to introduce. This is P channel MOSFET. It is of enhancement type. Okay, so this is drain, gate, source, and body. So it is of symmetrical device means this is drain terminal, this is source terminal. So this drain and source can be used interchangeably. That means we can replace this drain with the source and source with the drain. That's why it is called symmetrical device. It's similar to the one that is in JFET also. So JFET also we can uh, replace the drain and source terminals. So the JFETs are also a symmetrical device. But BJT is not a symmetrical device. So we cannot use BJT like a collector and emitter interchangeably, because this emitter and collector is having different doping concentrations, and also these two are having different width or different area. So the emitter is having less area and collector is having higher area. So in case of BJTs, we have seen this is like this. This is collector, this is emitter, and this is base. So we cannot replace emitter and collector because collector is having higher area and emitter is having lesser area. And this doping is also different in both the cases. Emitter is having higher doping and this is having moderately doping. Okay, so this cannot be interchangeably used. Okay, It is non-symmetrical device. BJT is a not symmetrical device. Okay. Next point we can write here. In case of BJT and MOSFET, MOSFETs use a lesser area compared to a BJT. If the BJT area is 100, then the MOSFET area will be 5 or less than 5 also. Okay. So there is very large difference in case of area. So this MOSFET is very much smaller in comparison to BJT. So if MOSFET is very much smaller, the chips made by MOSFET will be having higher density. Okay, so the chips made by MOSFETs will be of higher density. Okay, so here high density chips can be fabricated by using MOSFETs. Okay, in depletion we have already seen. In depletion type MOSFET, it is having pre-existing channel. Okay, and in enhancement, no pre-existing channel. So these are the basic, some of the basic components. Now we will see like how the MOSFET is somewhat different from the JFET and BJT. Okay, so in case of the difference we can talk about. So here the MOSFETs are compared to be less noisy than the JFET. MOSFETs are less noisy than JFETs because in MOSFETs we are having 4 terminals. MOSFET is a 4 terminal device, but JFET is a 3 terminal device. So in JFET there is no body, but in MOSFET we are having body terminal. Okay, or the substrate terminal, and that is made to be connected to ground. So there is a less chance of noise in case of MOSFETs. Okay, so because of substrate grounding, that means the substrate terminal is there and that is made to be grounded always in case of n-channel MOSFET. So that's why this JFETs are compared to be more noisy than the MOSFETs. Okay, and also here MOSFETs are compared to be uh, more faster, or it is MOSFETs are faster than the JFETs basically. Okay, so here MOSFETs are compared to be faster than JFET in comparison to BJTs also. In comparison to BJT also, these MOSFETs are faster than the BJTs also. Okay, so from these two, it will be showing a faster speed the MOSFET. So in BJTs basically, in BJTs there is a minority carrier storage time is there. Okay, minority carrier storage time, that is like suppose it is represented by ES. So because of the minority carriers, there is a minority carrier storage time. So this will basically results in higher switching in case of BJT. Okay, so it results in higher switching time. Higher switching time means it will be taking large time to make the switch between 0 or 1 or between changing the states. This BJT requires larger switching time. But in case of MOSFETs, there is no minority carriers. Okay, so there is no minority carriers in MOSFETs because it is a monopolar device. Okay, so only the majority will be constituting the current flow, but there will be no concept of minority carriers. Okay, so if there is no minority carriers, then there will be no there will be no minority carrier storage time. So as it is having no minority carrier storage time, hence switching time switching time in MOSFETs will be smaller. So switching time is smaller. That means speed is fast. Okay, so the MOSFETs will be having faster speed because it is having no minority carrier switching time. So we are going to compare the MOSFETs in case of BJT. From the switching time, we can consider like uh, MOSFETs is relatively more suitable for high frequency applications. So if we are going to operate the device, either MOSFET or BJT, in case of high frequency applications, then MOSFETs will be preferred. MOSFETs are preferred for high frequency applications. Okay, so this will be preferred for high frequency applications. These are the basics of MOSFET in comparison to BJT and JFETs. Next, we will now differentiate between the depletion and enhancement MOSFET. Okay, so here depletion MOSFET in depletion MOSFET. So this depletion MOSFET is similarly equals to a JFET only. That means in JFET, what we have seen is the maximum current that can flow, maximum drain current that can flow was equals to IDSS. So in case of depletion type MOSFET also, the maximum current that is possible is IDSS. Okay, so this is drain to source, safe current, or drain to source saturation current. Safe current, or I call it or saturation current. So drain to source saturation current or safe current. So in case of depletion MOSFET, the maximum current that can be flowing is IDSS. So in case of JFET also, the maximum current was possible is IDSS only. Okay, so here the ID will be equals to IDSS, or it will be less than IDSS. So always in case of depletion, because it is going to be operated in depletion, that's why it is having a fixed maximum current when there is no depletion. That means the gate to source voltage is zero. If we are going to apply the gate to source voltage, the current will be reducing from the maximum current. Okay, so this ID will be either equals to IDSS or it will be less than IDSS. Okay, but in case of enhancement type MOSFET, the current that will be flowing at the start of the operation is basically that will be the minimum current. Okay, so here the minimum current or minimum ID current will be IDSS. Okay, so this IDSS will be minimum in case of enhancement mode, and as we are going to apply the gate to source voltage in the forward bias case, the ID will be greater than IDSS. So it will be either equal to or greater than ID. This is the basic that we can differentiate between depletion mode and the enhancement mode. So this JFET, we already know JFET is always operated in depletion mode only. Okay, but this N-channel depletion MOSFET or P-channel depletion MOSFET can operate in depletion as well as the enhancement mode. That's why depletion type MOSFET, also called DE MOSFET, or sometimes it is called dual MOSFET, because it can operate both in enhancement as well as the depletion mode. That's why it is called depletion dual MOSFET. Okay, in case of NMOS and PMOS, the NMOSFET is preferred than PMOS. So why this preference is there? Because in case of NMOSFET, the mobility is given by mu n. In case of P MOSFET, the mobility is given by mu p, and we always know this mu n is greater than the mu p, and this mu n, if mu n is greater than mu p, that means the speed, in terms of speed or in terms of performance, we talk about N MOSFET. The N MOSFET will be providing the better performance than the P MOSFET. Okay, if both are having same size, then N MOSFET will be providing better performance. Okay, so that's why N MOSFET is preferred than the P MOSFET. Okay, because the mobility of electrons are greater compared to mobility of holes. Okay, but in case of fabrication point of view, PMOS PMOS is considered to be PMOS is considered to be easy for fabrication. Okay, PMOS is easy to fabricate compared to N MOSFET. But overall, if we uh, talk about here, the N MOSFET is having better performance. So in terms of better performance, it can have better performance in less area. If we want to have both similar performance, then PMOS is size doubled, or PMOS is requires twice the area that is required for the NMOS to provide the same performance. So if PMOS needs to be performing in comparison to NMOS, then PMOS should be sized twice the area of the NMOS. In case of fabrication, the PMOS is easy to fabricate. And why? Because in NMOS there is a problem called ion contamination problem. Because of this, while fabrication, there is no ion contamination problem in case of PMOS. That's why this PMOS is considered to be easy to fabricate, and in NMOS there is a problem, so it is not easy to fabricate. So as we say, like, the PMOS needs to be size double to provide the same performance than the NMOS. So PMOS is considered to be bulky, but it is cheaper in comparison to the NMOSFET. So because the PMOS is having bulkier size, but NMOS is of a smaller size than the PMOS. So in case of the fabrication point of view, if we talk about, the NMOS have the higher chip density. Okay, so higher chip density means it can store more information in the smaller area. Okay, so this is the main advantage in comparison to PMOS. We can say, you can write like NMOS has higher packing density. What does it implies is it can store more information in the smaller area. So on the smaller area, it can store more information. Okay. So in terms of like NMOS and PMOS, we have also seen. So separately, we have seen NMOS and PMOS. If we talk about the uh, CMOS, so one concept we you might have known what is CMOS. So CMOS is basically made up of PMOS as well as the NMOS. Okay, so any IC that is or any circuit that is made up of NMOS as well as the PMOS, that is called CMOS, that is called complementary MOSFET. That means whatever circuit is there, that circuit can be made up of NMOS. Okay, along with that, the same circuit can be implemented by the PMOS also. So by using PMOS and CMOS, the overall if a circuit is made that is having the PMOS as well as the here inputs are there, okay, and here output is there. So here NMOS as well as the PMOS is used to fabricate the circuit. So this is called a CMOS circuit. Or in terms of this is in terms of circuit. In terms of device we talk about. So PMOS. So PMOS is simple. Suppose this is a MOSFET. Okay, so only a single MOSFET is there here. This will be a gate. This is gate. This is drain, and this is source, and this is your body terminal. Okay, suppose this is of P type, then it will be an N channel. Okay, so N channel MOSFET is there, or NMOS is there. Suppose this is. Similarly, we can fabricate another P channel MOSFET. Okay, PMOS we can fabricate. But if a device is there that can have both NMOS as well as the PMOS at the same channel on the same IC or on the same substrate. Okay, so this is here. Suppose this is here. It is of P type. Okay, and here this is source, and this is gate, and this is drain, and this is your body. So this is your NMOS. So up to here, this is NMOS. But on that P type substrate only, it is called N well. So P type here it is called N well. On N well, this is of N type. This will be of N type. So here again another MOSFET will be fabricated. So this MOSFET will be your gate, source, and drain. So a this is a PMOS, and this is a NMOS. So on a single substrate, we are having both NMOS as well as the PMOS. Okay, so this combination is called CMOS, and this single one is called either PMOS or NMOS. So PMOS and NMOS can be fabricated by a single substrate separately, or we are able to design this CMOS circuit. That means PMOS and the NMOS can be fabricated on the same substrate. This is called the CMOS technology. So here by using the CMOS technology, we are going to reduce the area required for designing the circuit. That means it provides very high density. Very high density. Okay, so very high density means it can accommodate large number of transistors on a smaller area. That means if it is able to accommodate large number of transistors on a single or a smaller area, it can store more information on less area. Okay, that's why this CMOS technology is most frequently used for circuit designing in case of the low power requirement and also the smaller area requirements. So in case of MOSFET, suppose we are going to have a fabrication of MOSFET. Okay, so we can write like construction of so MOSFETs. Okay, So MOSFETs construction we can just see from here. So we are having up two different type of MOSFETs, depletion and the enhancement mode. Okay, so we are having depletion as well as the enhancement. So the similar construction in case of both are there. The only difference is like in case of depletion one we will be uh, depositing the channel region while we are fabricating the device. Okay, but in case of enhancement type MOSFET we will be fabricating such that the channel will be formed as we are going to apply the uh, voltage terminal or gate voltage is basically gate source voltage we are going to apply. Then there will be uh, formation of channel will be there in case of uh, depletion one. Okay, so the basic fabrication steps is like we will first take a substrate. Okay, so we will be taking a substrate. Suppose we want to fabricate a PMOS. Okay, then substrate that we will be taking is of N type. If we want to fabricate an N MOSFET, then the substrate that we will be taking is of P type. So suppose we are going to fabricate an N MOSFET. Okay, so if we are going to fabricate an NMOS, then substrate of P type substrate we will be taking. Substrate means a base on which we will be depositing further layers. This is your substrate. On this substrate, we will be having two regions. One region for source and drain. Okay, so this is of P type. So this is P type substrate is there. So its opposite, like it is N type will be there, but N type with highly doped. Okay, it is highly doped N type regions will be there that will be used for source and the drain region. And the gate region is having here, so there will be oxide. So this is oxide, and an oxide is there, and over that we will be having the gate terminal. Okay, so it is metal. So this is metal. So it is gate terminal. Okay, and this uh, N type will be connected with a terminal that is bimetal. It is considered to be source, and this is considered to be drain. Okay, and this here a metal layer will be there at the bottom. So metal layer is basically used for making the connections. Whenever we are going to use the metal, we are going to make a connection. So at the bottom there will be a metal layer. So this metal layer will be connecting. So this will be a terminal called body. Okay, so this region is of P type. So this is a terminal called body, and this is your drain, and this is gate, and this is your source. Okay, so this channel region, in case of depletion type MOSFET, we will be uh, making this you can say a highly doped this region. We will be making further doping in this region so that there will be a predefined channel will be there. But in case of enhancement type, there will be we will not be performing any type of doping here, so that whatever P type is there, the same substrate will be looking like here. But as we are going to apply the gate to source voltage, with respect to that, there will be accumulation of charges will be taking place. Okay, so that charges, like if we are going to apply the positive gate voltage, here electrons will be depositing. So as electrons will be depositing, it will be forming the channel. So n type region is there, here n type region is there. So here electrons are in majority, here also electrons are in majority. So as we are going to apply the gate terminal that is of positive voltage, or like we are going to forward bias this region, then it is like going to attract the electrons here. So as electrons will be attracted, there will be accumulation of electrons that will be forming the channel region. So then as we are applying the drain to source voltage, with respect to that, the electrons will be moving between source to drain. So this will be constituting the current flow. So this is how the current conduction takes place in case of MOSFETs. So similarly, if we talk about the depletion type MOSFET, so there will be predefined inversion charge regions are there. So that means this is the case of like enhancement type NMOS. Okay, so if we talk about the uh, PMOS, okay, so in PMOS what will be there, like in case of enhancement type, suppose NMOS is there, but in case of enhancement type, so if that is the case, so here we will be making similar arrangements. Okay, this is N plus N plus, and this is your P type substrate is there, and here this is gate. So this gate will be having an oxide, so there is oxide, and this is your metal, gate terminal, source terminal, and drain terminal, and this is your body. So in the depletion type, suppose MOSFET is there, this is depletion type and MOSFET is there. So here predefined electrons will be there here. That means uh, charges will be available here in previously. That means as we are going to apply the negative terminal between gate to source, so as we are going to apply the negative terminal, the positive electrons will be coming out here. So initially there will be electrons, so there will be a channel formed. Already there will be a channel. Okay, so already there is a channel, and that channel is having electrons available into that. Okay, so electrons are available already. We will be making sure by using the doping, or by using the doping we will be providing the electrons here, more electrons, similar to N plus region. So N plus region is having majority electrons. Here also electrons are there. So whatever gate, suppose gate is 0, then the maximum current will be flowing. So as we are going to apply the gate, that is VGS less than 0, that means we are going to apply negative here. So as we are going to apply negative here, the positive will be attracted in the channel region. So here positive electrons will be attracted. So as positive electrons will be attracted, positive charge carriers will be attracted into this channel region. So it is going to replace the electrons, because previously it is having electrons, but now it is not having the electrons. It is positively charged ions are there in between the N plus and N plus. So it is going to obstruct the channel. It is going to, you can say, replace the channel with positively charged ions. So that's why it will be like, once it is replaced by another charge, positive charge immobile ions, there will be less number of electrons available between the channel. So as there is less number of electrons available in the channel, less current will be flowing between drain to source. So as we are going to apply the gate to source voltage that is less than 0, there will be less charge available, less electrons available into this channel region, and electron concentration is less. So less electrons will be moving from source to drain, so there will be less current constituted in case of depletion type of MOSFET. Okay, so this is the basic concept in case of enhancement and the depletion type of MOSFET.